Okay, in this video, I just want to point out that the change of variables extends to three-space and to triple integrals as well. So if I had some blobular region in the xyz space called R, and I was trying to do a triple integral of some function over R with respect to volume in the xyz system, if I had a nice region S in the UVW coordinate system, and a transformation that was C1, so the first derivatives were continuous, and 1-to-1, so I can go back and forth, okay, that maps this region S to this region R, then I could integrate over S instead. And of course, the integrand I get by just doing a composition. I take UVW, I plug it into T to get a point XYZ, and then I plug it into F to get the original integrand. Then I have a scaling factor, and that scaling factor, once again, is just the absolute value of the Jacobian. The difference is that here, the Jacobian is going to be the determinant of a 3-by-3 matrix. And once again, it's going to be contain all of these partial derivatives, where what we're going to, which is xyz, is going to go in the rows, and what we're mapping from, which is uvw, is going to go in the columns. Okay. I'll also point out, it's really important that we are thinking of this as we're going from here to here. That helps me remember that in my derivatives, the x, y, and z's are on top because they're the outputs, and the u's and w's are on bottom because they're the inputs. Okay, so that's the general summary. Let's just do one quick example in 3-space. What I want to do is I want to find the volume enclosed by x squared over 4 plus y squared over 9 plus z squared over 25 equals 1. So this is just an ellipsoid in 3-space, and let's see, it's gonna look something like so, and I want to try to find the volume of that. So I'm going to call that my region R. And I know this would just be the triple integral over R of 1 dv in the xyz system. But I'm not super crazy about having an ellipsoid here. I'm going to borrow off the last example. I'm thinking if we take S to be just our unit sphere, that I can map S to R by simply saying, okay, this was in the UVW system. So the u-axis corresponds to the x-axis, which got stretched by a factor of 2. So let's let x be 2u. Okay. The v-axis corresponds to the y-axis, which got stretched by a factor of 3. So y is going to be 3v. And the w-axis corresponds to the z-axis, which got stretched by a factor of 5. So z is going to be 5w. And that does work. All the work that we did in the last example where we had a disk mapping to a region enclosed by an ellipse generalizes now that we're in 3-space. Okay. I do want to remember that this 4 is 2 squared, so that's saying that we're coming out 2 and going back 2 in the x direction. 3 and 3, 5 and 5. Okay, I'm liking it. So, let's see. If I take a look at del xyz, del uvw. Okay. That's going to be the determinant. So the Jacobian is the determinant. The scaling factor is the absolute value of that determinant. So I'm looking at the partial of x with respect to u, partial x with respect to v, partial x with respect to w. Partial of y with respect to u, partial of y with respect to v, partial of y with respect to w, partial of z with respect to u, partial of z with respect to v, partial of z with respect to w. But this is a ridiculously nice matrix because x depends only on u, so the other two partials are 0. Y depends only on v, the other two partials are 0. Z depends only on w, the other two partials are 0. The determinant is just 2 times 3 times 5. It's 6 times 5, which is 30. It's a nifty shortcut if you have a diagonal matrix. To see why that works, notice that if I were to expand along the first row, I would get 2 times the determinant of 3005 plus 0 copies of something plus 0 copies of something. But this determinant is just 3 times 5. So I end up just getting 2 times 3 times 5, which is 30. So we're going to have the triple integral over S of, our integrand was 1. That's not changed. My scaling factor is 30. Oh, let's actually remind ourselves that the absolute value of 30 is 30. We're taking the absolute value of that Jacobian. And then this is dV in the UVW system. Well, that's just 30 times the volume of S. Now, to find the volume of S, I could say, I know that. It's 4/3 pi times the radius cubed. And since the radius is 1, that's 4/3 pi. So this is just going to be 40 pi. I mentioned a while ago, if you remember that that's the formula of a volume of a sphere, when that shows up as part of a larger problem, you can just use that. Now, if you didn't remember that, that's totally fine. You could get this. I would switch to spherical coordinates. And U, V, and W are just names. U's in the role of X, V's in the role of Y, W's in the role of Z, although you could interchange that if you wanted to, okay? But basically, I would just be integrating rho squared sine phi over the, times 30, obviously 30 times integrating rho squared sine phi over the limits for the unit sphere. Rho goes from 0 to 1, phi goes from 0 to pi, theta goes from 0 to 2 pi. Very nice to see.